Hello and welcome. Today we are diving into one of the most powerful, fundamental ideas in all of modern AI, embeddings. This is the concept that allows a computer to finally get its head around not just the letters in a word, but the actual shape of language itself.
So let's just start with a really simple question. Think about it. How can a computer possibly know that the word king and the word queen are related, and at the same time know that king and, say, cabbage are not? To us, it's totally obvious. But for a machine that just sees a bunch of text, how does it ever learn that connection?
Well, the answer lies in this really elegant concept called an embedding. And this is the core idea, the foundational trick that finally lets us turn messy, complicated human language into something a computer can actually understand and work with.
Okay, so what is it? At its heart, an embedding is basically a translator. It takes a word, like king, from a vocabulary that could have hundreds of thousands of words, and it translates it into a list of numbers, what we call a vector. But here's the key. It's not a random list. It's a very specific, very meaningful set of coordinates.
Now, you might see some formal math notation like this and, your eyes might glaze over a little bit, but stick with me, because it's actually pretty simple. All this is saying is that we have some function, we'll call it phi, that maps a word from our big vocabulary v into a point in some d-dimensional space. In other words, we're just giving every single word its own unique address on a giant multidimensional map. That's it.
So how does this translation actually happen? Well, you can think of it like a journey of compression. We start with our word, our token, let's say king. Now, a really basic way to represent it for a computer would be something called a one-hot vector. Just imagine a list with, 100,000 slots, one for every word in our dictionary. It's all zeros everywhere except for a single one at the one position that stands for king. As you can imagine, this is hugely inefficient, and it tells us absolutely nothing about what the word means. So the embedding process takes this giant, sparse, kind of useless vector and compresses it down into a much smaller, dense vector, where every single number is actually meaningful.
And really, this contrast is what it's all about. On one hand, you've got that one hot vector. It's massive, it's almost completely empty, and the position of that single one doesn't really mean anything. But on the other hand, you have the dense embedding. It's compact, it's efficient, and every single value inside of it helps to encode the very essence of what that word is all about.
So if you're looking for the best way to think about this, here it is. Just forget all the math for a second and picture a vast, multi-dimensional space. Embeddings create a coordinate system, a map, where every single word we know gets its own specific location. In a very real sense, language literally becomes geometry.
Okay, so we're building a map for words. Great, but that raises a pretty obvious question, right? How on earth does the system learn where to put everything? How does it figure out the right coordinates for hundreds of thousands of different words?
Well, the core principle behind it is actually incredibly simple and intuitive. It's all based on the old saying that a word is known by the company it keeps. Words that show up in similar sentences in similar contexts, like dog and cat, both appearing near words like pet or food, well, they should probably have similar meanings. And if they have similar meanings, they should be placed close to each other on our map.
When you get right down to it, the whole training process really just boils down to this. The model reads billions and billions of sentences, and for every word, it looks at the words around it. And the goal is simple. Adjust the coordinates on the map to push words that appear together, the real pairs, closer to each other. And at the same time, push words that don't appear together, the random pairs, further apart. It's just a constant game of push and pull, over and over again.
Now, under the hood, there's a really powerful mathematical shortcut that makes this all possible and efficient. It turns out that this entire learning process is mathematically the same as taking a giant table, a matrix, of how often words appear together, and then using a clever trick to break it down and find all the underlying relationships. This process, called matrix factorization, is really the engine that learns the entire word map for us.
All right, this is where it all pays off. This is the fun part. We've gone to all this trouble to build our map. We have coordinates for every single word. So, what can we actually do with it? This is where the magic really starts to happen.
Because words are now just points in a geometric space, we can actually do math with them. It's amazing. So think about this classic example. What do you think happens if we take the coordinate for the word king? Then we subtract the coordinate for man, and then we add the coordinate for woman. What new point on our map do we land on?
The result is the vector, the coordinate that is closest to the word queen. Just think about that for a second. That's incredible. It means the model hasn't just memorized definitions. It has actually learned the relationship between words. That direction from man to woman represents a concept, like gender, that it can now apply to other words.
So the crucial takeaway here is that this new geometric space has rules. The distance between any two word points tells us how similar their meanings are, so cat is going to be way closer to dog than it is to car, and the directions, or the offsets between points, they encode these abstract relationships like gender, or verb tense, or even things like country to capital.
Now, this core idea is absolutely the foundation of everything. But as you might expect, it has evolved a lot. So let's look at the really crucial difference between that classic approach and how modern AI systems, like transformers, handle all this.
You see, those early models like Word2Vec gave each word a single static coordinate. The word bank always had the exact same address on the map, no matter what sentence it was in. But modern AI models create what we call contextual embeddings. The vector for the word bank actually changes depending on the sentence it's being used in.
And this example shows you perfectly why that's so powerful. A word like bank has totally different meanings, right? And a modern model gets that. When it sees riverbank, it generates one vector. But when it sees money from the bank, it generates a completely different vector, one that captures the precise meaning for that specific context. And that is a massive leap forward in understanding language.
So why are we spending all this time on this one concept? Why is it so important? Well, it's because embeddings aren't just some clever little trick. They are the absolute bedrock, the foundation on which all of modern natural language processing is built.
So let's just do a quick recap of the key insights. On a technical level, embeddings are a form of matrix factorization. On a conceptual level, a word's meaning is just its position relative to all the other words. Relationships between words become simple directions on a map, and the overall geometry of this entire space ends up revealing the hidden structure of language itself.
If you only take away one thing from all this, let it be this elegant little summary. An embedding brings together three really powerful ideas. It's a form of compression, turning huge, useless data into something useful. It's geometry, turning language into a map we can navigate. And it's all based on probability, learning from how often words appear near each other.
And this brings us to the final crucial point. That attention mechanism you hear about, the engine that lets models like ChatGPT understand context and generate such coherent text, it works by looking at the relationships between words in this geometric space. Without embeddings to create that space in the first place, the whole thing just can't exist. The entire architecture of modern AI as we know it would fall apart. It all starts right here, by giving language its shape.